Uncle. This is a sample DEA Excel sheet that I have prepared, which contains various input and output parameters that I have considered. So this is just a sample that I have considered, and we can modify this Excel to contain the actual values of Techser. So when you open this Excel sheet, you can see two tabs, what is input and input oriented and output oriented. So first I'll explain the input oriented, and then let's go to output oriented. So in the input oriented model, what we try to do is we find out the efficiency of a particular unit by keeping the output constant and how much percent we can reduce the utilization of input to obtain the same output. So it's just like telling we'll keep the output constant, but we'll try to see how much we can minimize the usage of input in order to get the same output. So first, to run this DEA, we need to download, or we have to add one add-in that's already available in Excel. So for that, let's go to File. In that, you have to go to Options. In that, Add-ins. And here under Manage, you have to select Excel Add-ins. Then click on Go. Here there are various add-ins available. In that, you have to click Solver add-in and say OK. So this particular add-in, which will help us compute this linear programming model, is added. So if we go under the Data tab, there is Solver add-in added. So this is how it looks. So coming to the parameters, all the ones that are in green are the input parameters, and the ones that are in black are the output parameters. So I have considered for this for test that let there be 7 different units, and I have just given random values, and I have given formulas in each cell which can be known here. So if you click on this cell here, you'll know what the formula is. So but for you to do it, you don't have to worry about the formulas because it is already there. So what you can do is you can just change this. Let's say instead of total revenue, you want to keep it as total percentage revenue. So you just have to edit this, and you have to go on editing the values in each unit, so that this formula will automatically consider the new values that has been added. Let's say, okay, this is, then I'll change this to so similarly, in case you have more inputs than that's mentioned here, what you can do is you can just right click on insert. You can type in whatever additional input that you have and go on typing the values here. So here the formula is automatically taken into consideration because the formula is also copied. So now to run this, okay, before that, here the weights that have been given is telling that all these units have given equal weightage. That means the priority is the same, and I don't consider any one unit more than the other. So we are giving equal weights to all the units that's there. This objective is something that's being used for to calculate DEA, and the values initially we have to give 111 for each unit. So among this, let's consider any unit that we have to compare or we have to find the efficiency in relative to in relation to all other units. So let's randomly take this unit So what we are doing here is we are finding out the efficiency of this unit in relation to other. That is the relative efficiency of unit 5 with respect to units 1 to 7. So once the values have to be copied from unit 5 to reference values here. So what I just did is I'll repeat the step that, okay, so for that first I'll delete this. From unit 5 I copied the values and I'm pasting under ref values section. So now to run the solver we have to make sure that the values are 1 for all unit, and the cell that is highlighted in yellow is the place where you'll get the efficiency score of unit 5 with respect to all other units. So let's run the solver. So in the solver, the linear programming model that I have considered is the objective is to find the efficiency that's there in cell here. This is cell J14, and I'm trying to find out the minimum usage of the input in order to obtain the same output. So I'm using minimum value here, and the variable cells or the decision making cells are the ones that are there here. So what's been given in this values here, those are the decision making cells. So these values have been changed. I'll set again. So here the objective is find the efficiency of this given, minimum given, by changing the variable cells B15 to I15 and subject to constraints. Here J13, that is this cell, I have to make sure that it's always equal to 1 because it's one unit that we are finding the efficiency of. So here I've already given the formula, that's why it is represented as 7 here. So once you run the solver, it automatically makes sure that the J13 value has value 1 and J3 to J8. So these are the ones. So what you're trying to do here is you're trying to find out if these values are greater than or equal to RHS. That means it's just like telling that, okay, we are finding out the efficiency of unit 5. Its input parameters or the input values should be greater relative to all other units that is there. So that's why the inputs have to be used up to the maximum here and the outputs to be used to the minimum, then only a unit can be called as efficient. So those are the constraints that I have given in the solver that can be seen here. So for this I have used the simplex linear programming model. So let me run the solver for unit 5 in comparison for all other units. So I'm going to solve it. So after solving, I received a value 0.912. That means compared to all other units, unit 5 is 91% efficient. So similarly, we can go on finding out for each unit. So what's its relative efficiency compared to the other units? So again, I'll go to solver, and every time I have to just click on solver and click on solve. So this will calculate. So here the value given is 1. So this means unit 1 is 100% efficient when compared to all other 7 units. So similarly we can go on doing this for each unit. So let's take another unit at random. Let's say unit 4. So I copy the values, I place it in ref values, then again So I have to ensure that the decision variables, that is the values, have to be 1. So I make it 1. Now I run the solver. Okay. So this also has shown that unit 4 is 91% efficient. So to attain maximum efficiency, what is to be done? So let's copy this ref values here and the values that has been obtained here. So what does this mean? So we'll ignore the outputs for now because we are trying to only calculate how much input is to be used so that the unit becomes efficient. So what are we doing here in comparison? So now I'll see this is unit 4's actual input values. Now this is the efficient units values. So what is to be done is, I'll copy this. So what's to be done is percentage revenue. So it is 1312.82 now. If percentage revenue is increased to 1445.29, then this unit can approach being efficient. Similarly, this is the actual value now, this is the expected value. As the actual value becomes closer to the expected value, then a manufacturing unit can become efficient. So in this way we can know that which parameters have to be increased to what value so that the efficiency of the unit increases. So similarly, like this we can do for unit 6. So I'm copying the ref values here and I have to ensure before I run the solver the decision variable set as solver is 1, and then I click on solver and I solve it. So here again we got the efficiency as 1, that means unit 6 is efficient. So if you check the values here and here, so they're almost same. That means for unit 6 nothing has to be done, it's already efficient. So let's see for some other unit, unit 2. So even unit 2 is efficient. Let's go back to unit 5. So I run the solver again, so the efficiency is 91%. So let me copy the values here, only the input values I'm copying. So this again means that for percentage revenue, the current value is 1073. So if it is increased to 1465, it moves towards becoming efficient. So similarly, when all the input parameters are becomes closer to the expected values, then it becomes more efficient. So in this way, this study help us to find out which input parameter has to be increased to what level so that the so that the unit becomes efficient.